Welcome to Earthly Teachings, where learning is clear and powerful. Today, we are working on Mathematics N6. Let's learn together. In this video, we'll dive deep into the world of moments and centroids. This is a fundamental concept with applications in many fields like engineering and physics. By the end of this tutorial, you will be able to define what a moment and a centroid are, and most importantly, you will be able to calculate the coordinates of a centroid for complex areas using integration. These calculations are a key part of the N6 syllabus, and mastering them will be a great accomplishment. So, let's get started. First, let's understand what we mean by moment. The moment of a physical quantity is a measure of its tendency to cause rotation about a point or axis. It's the product of the quantity itself and its perpendicular distance from that point or axis. Think of it like using a spanner to turn a bolt. The harder you pull on the spanner, the greater the force. This is our quantity. The further away from the bolt you hold the spanner, the greater the distance. The twisting effect, the moment, gets larger if you increase either the force or the distance. We can have different orders of moments. A first moment is a quantity multiplied by the distance. A second moment, also known as the moment of inertia, is the quantity multiplied by the square of the distance. For our N6 work, we will focus primarily on the first moment of area. The reference axis is simply the line or axis about which we are calculating the moment. In most of our problems, this will be the x-axis or the y-axis. Now let's move on to our second main concept, the centroid. The centroid of an area is the geometric center. It's the balancing point of a two-dimensional shape. If you have a thin, uniform sheet of metal, you could balance it perfectly on the tip of your finger placed at its centroid. We denote the coordinates of the centroid with x bar and y bar, so the centroid is the point x bar, y bar. For shapes with symmetry, the centroid is easy to find. For example, for a circle, the centroid is right at its center. For a rectangle, it's where the diagonals intersect. And for a triangle, it's the intersection of the medians, which are lines from each vertex to the midpoint of the opposite side. But what about irregularly shaped areas? This is where integration comes in. If an area has one axis of symmetry, like a semicircle, we can find one coordinate by inspection, but the other one requires calculation. For areas with no symmetry, we must calculate both coordinates using the methods we'll learn today. So how do we actually calculate the centroid coordinates? We use these fundamental formulas. The x-coordinate of the centroid, x bar, is the area moment about the y-axis, a sub my, divided by the total area, a. Similarly, the y-coordinate of the centroid, y bar, is the area moment about the x-axis, a sub mx, divided by the total area, a. These are the two main formulas you need to remember. Let's break down each component. First, the area A. You've already learned how to calculate the area between curves using integration. We'll be using that skill extensively here. Second, the area moments, a sub mx and a sub my. A sub my is the area moment about the y-axis. It's the first moment of the area with respect to the y-axis. A very important note. A sub my should be read as area moment about the y-axis, not area m minus y. This notation simply indicates the axis of reference. To calculate these moments, we use another integral, the integral of r times dA. Here, r is the perpendicular distance of a small element of area, dA, from the reference axis. dA is our differential element of area, which we will define using either a vertical or a horizontal strip. Let's explore how to find r and dA for both types of strips. Let's first consider using a vertical strip. A vertical strip is a thin rectangle with a width of dx and a height of y. It extends from the lower boundary of the area to the upper boundary. The area of this strip, dA, is its height times its width. So, dA equals y times dx. If the strip is between two curves, y1 and y2, the height is y1 minus y2. So dA equals y1 minus y2 times dx. This is a crucial formula to remember. Now let's find the distance r for this strip. For the area moment about the y-axis, a sub my, our reference axis is the y-axis. A vertical strip is parallel to the y-axis, and its distance from the y-axis is simply its x-coordinate, so r equals x. For the area moment about the x-axis, a sub mx, Our reference axis is the x-axis. A vertical strip is perpendicular to the x-axis. We need the distance of the centroid of the strip from the x-axis. This is the midpoint of its height, which is y1 plus y2 divided by 2. Now we can put these pieces together to get our integration formulas. Similarly, we can use a horizontal strip. Let's see how that works. A horizontal strip is a thin rectangle with a height of die and a width of x. It extends from the left boundary of the area to the right boundary. The area of this strip, dA, is its width times its height, so dA equals x times d. If the strip is between two curves, x1 and x2, the width is x1 minus x2, so dA equals x1 minus x2 times di. Now let's find the distance r for this horizontal strip. For the area moment about the x-axis, a sub mx, our reference axis is the x-axis. A horizontal strip is parallel to the x-axis, and its distance from the x-axis is simply its y-coordinate, so r equals y. For the area moment about the y-axis, a sub mi, our reference axis is the y-axis. A horizontal strip is perpendicular to the y-axis. We need the distance of the centroid of the strip from the y-axis. This is the midpoint of its width, which is x1 plus x2 divided by 2. Putting these together, we get our horizontal strip integration formulas. For a sub mx, we integrate y times x1 minus x2 di. For a sub my, we integrate x1 plus x2 over 2 times x1 minus x2 di. This simplifies to the integral of 1/2 times x1 squared minus x2 squared. You might be wondering, which strip should you use? The answer is, choose the one that simplifies the calculation the most. Look at the shape of the area and the equations of the curves. A vertical strip works best when the upper and lower boundaries are clearly defined as functions of x. A horizontal strip works best when the left and right boundaries are clearly defined as functions of y. We'll see examples of both. We've built up all the necessary tools. Now, let's put it all together into a step-by-step process for determining the coordinates of a centroid. Step 1 is to find the total area, A, of the region. This is calculated using the definite integral of y1 minus y2 with respect to x, or the integral of x1 minus x2 with respect to y, depending on the strip you choose. An important exam strategy: always draw a clear diagram. It helps you identify the correct limits of integration, which function is the upper or right one, and which type of strip is most appropriate. A good diagram can prevent mistakes. Step 2 is to find the area moments, a sub mi and a sub mx. You'll need to calculate both to find the full centroid x bar, y bar. Remember to use the correct formulas for r and dA based on your chosen strip orientation. And finally, step 3 is to substitute the values you found in steps 1 and 2 into our original centroid formulas. X bar equals a sub my over a, and y bar equals a sub mx over a. If you follow these 3 steps carefully for each problem, you'll be well on your way to success. Let's practice with our first example. Here's our first example. We need to determine the coordinates of the centroid of the area bounded by the curves y equals sin x and y equals ksx, and the line x equals pi over 2 for the interval from 0 to pi over 2. Our first step is always to sketch the graph to visualize the area. Let's draw our x and y axes. We're interested in the interval from 0 to pi over 2. The curve y equals cos x starts at the point 0, 1 and crosses the x-axis at x equals pi over 2. The curve y equals sin x starts at 0, 0 and goes up to the point pi over 2, 1. These two curves intersect at the point where sin x equals cos x, which is at x equals pi over 4. Here y equals the square root of 2 over 2, or approximately 0.707. The area we are interested in is the region enclosed by these two curves between x equals pi over 4 and x equals pi over 2. We'll shade this area to be clear. This is the area for which we need to find the centroid. Now we need to choose a strip. A vertical strip seems most appropriate here because for any given x value, the upper curve is always y equals sin x and the lower curve is always y equals cos x. This makes it easy to define the height of our strip. So we'll use a vertical strip with width dx. Let's label a typical vertical strip. Its width is dx and its height is the upper curve, y1 equals sin x, minus the lower curve, y2 gato equals cos x. We've sketched our graph and chosen a vertical strip. Now let's execute our three-step process. Step 1. Find the total area A. The area A is given by the integral of y1 minus y2 dx. Our upper curve is y1 equals sin x, and our lower curve is y2 equals cos x. The limits of integration are from pi over 4 to pi over 2. Now we integrate. The integral of sin x is negative cos x, and the integral of negative cos x is negative sin x. So our antiderivative is negative cos x minus sin x. Let's evaluate this at our limits. We plug in pi over 2, then subtract the result of plugging in pi over 4. This gives us negative ga, cos of pi over 2 plus sin of pi over 2, minus the quantity negative, cos of pi over 4 plus sin of pi over 4. We know cos of pi over 2 is 0 and sin of pi over 2 is 1. Cos and sin of pi over 4 are both the square root of 2 over 2. Substituting these values, we get negative 0 plus 1 minus negative square root of 2 over 2 plus square root of 2 over 2. This simplifies to negative 1 plus the square root of 2. Calculating this gives us an area of approximately 0.4142 square units. Now that we have the area, let's move to step 2, calculating the area moments. We'll start with the area moment about the y-axis. The area moment about the y-axis, a sub mi, is the integral of r times dA. For our vertical strip, the distance r from the y-axis is x, and dA is sin x cos x dx. So we need to evaluate the integral from pi over 4 to pi over 2 of x times sin x cos x dx. Notice the product of x and trigonometric functions inside the integral. This is a classic case for integration by parts. Recall the integration by parts formula. The integral of u dv equals uv minus the integral of vd. Here we'll let u equal x and dv equal the quantity, sin x minus cos x dx. Differentiating u gives us do equals dx. Integrating dv gives us v equals negative cos x minus sin x. Now we substitute these into the integration by parts formula. This simplifies to negative x times the quantity, cos x plus sin x, plus the integral of cos x plus sin x. The integral of cos x is sin x, and the integral of sin x is negative cos x. So our full antiderivative is negative x times cos x plus sin x minus cos x. Now we evaluate this at our limits, pi over 2 and pi over 4. Plugging in pi over 2 gives negative pi over 2 times 0 plus 1 minus 0, which is negative pi over 2 plus 1. Plugging in pi over 4 gives negative pi over 4 times root 2 over 2 plus root 2 over 2, plus root 2 over 2 minus root 2 over 2, which simplifies to negative pi root 2 over 4. Subtracting the second part from the first gives us negative pi over 2 plus 1 plus pi root 2 over 4, which is approximately 0.5399 cubic units. Remember, area moment is distance times area, so the units are units cubed. We've found the area and the area moment about the y-axis. Now, let's find the x-coordinate of the centroid. The formula for x bar is a sub mi divided by a. We substitute our calculated values. A sub my is approximately 0.5399, and a is approximately 0.41142. Dividing these gives us approximately 1.303 units. Great, we have x bar. Now we need y bar, which means we must first calculate the area moment about the x-axis. A sub mx is the integral of r times dA. For our vertical strip, the distance r from the x-axis is y1 plus y2 over 2. The dA is y1 minus y2 dx. So we integrate 1/2 times y1 plus y2 times the y1 minus y2. This simplifies to 1/2 the integral of y1 squared minus y2 squared dx. Substituting our functions, we get 1/2 the integral of sin squared x minus cos squared x dx. To integrate this, we'll use a trigonometric identity. We know that cos of 2x equals cos squared x minus sin squared x. Therefore, sin squared x minus cos squared x equals negative cos of 2x. Substituting this, our integral becomes 1/2 the integral of negative cos of 2x dx. The integral of negative cos 2x is negative sin 2x over 2. So we need to evaluate negative 1/4 sin 2x from pi over 4 to pi over 2. Plugging in the limits, we get negative 1/4 times the quantity, sin of pi minus sin of pi over 2. Sin of pi is 0, and sin of pi over 2 is 1. So this is negative 1/4 times 0 minus 1, which equals positive 1/4 or 0.25 cubic units. With the area moment about the x-axis calculated, we can now find the y-coordinate of the centroid. The formula for y bar is a sub mx divided by a. We substitute our values. A sub mx is 1/4 or 0.25, and a is approximately 0.4142. Dividing these gives us approximately 0.604 units. So we have both coordinates. The centroid of the area bounded by these curves is located at the point 1.3023, 0.604. This point should be inside the shaded area on our graph, and a quick look confirms it is in a reasonable position. This completes our first example. We have successfully used integration to find both centroid coordinates. Let's move on to our next example. This time, we'll find the centroid of the area enclosed by a parabola and the x-axis. Again, let's start with a sketch. This equation represents a parabola. Because the coefficient of x squared is negative, the parabola opens downwards. First, let's find the x-intercepts by setting y to 0. Factoring the quadratic gives us x equals 2 and x equals 1. These are where the parabola crosses the x-axis. The y-intercept is found by setting x to 0. This gives y equals 2. So, our parabola crosses the x-axis at 2 and 1, and the y-axis at 2. The area enclosed by the parabola and the x-axis is the region above the x-axis between x(2) and x(1). For this area, a vertical strip with width dx is the natural choice. Its lower boundary is the x-axis, or y equals 0, and its upper boundary is the parabola, y equals x squared minus x plus 2. We have our setup. Now for the calculation. Step 1. Find the area A. A equals the integral of y dx. Since our strip goes from y equals 0 to the curve, our y value is the function itself. The limits of integration are the x-intercepts, from 2 to 1. So we integrate the function from 2 to 1. Integrating term by term, we get negative x cubed over 3 minus x squared over 2 plus 2x. Now we evaluate this from 1 to 2. Plugging in 1 gives negative 1/3 minus 1/2 plus 2. Plugging in 2 gives positive 8/3 minus 2 minus 4. Subtracting the second from the first gives 9/2 or 4.5 square units. Now for step 2, the area moments. Let's find the area moment about the y-axis, a sub my. A sub my is the integral of x times y dt. We substitute e with the equation of our parabola. This gives us the integral from 2 to 1 of x times x squared minus x plus 2 dx. Distribute the x to get a simpler integral. The integral of x cubed minus x squared plus 2x dx. Integrating term by term, we get x to the power of 4 over 4 minus x cubed over 3 plus x squared. Evaluating this from 1 to 2 gives us negative 9/4 or 2.25 cubic units. Now for step 3, find the x-coordinate x bar. We divide the area moment we just found by the area we calculated earlier. This gives negative 2.25 divided by 4.5, which is negative 0.5 units. It's worth noting an exam tip here. For parabolas of the form y equals x squared plus bx plus c, the x-coordinate of the axis of symmetry is always at x equals negative b over 2a. In our case, this is negative 1 over 2 sur 1, which is negative 0.5. So, for symmetrical areas like this parabola, we could have found x bar by inspection, without needing to calculate the integral. It's a great way to check your work. We've found x bar to be negative 0.5. Now, to find the full centroid, we need to calculate the area moment about the x-axis, a sub mx. Using a vertical strip, the formula for a sub mx is 1/2 the integral of y squared dx. Remember, we are integrating y from 0 to the curve, so the full y is the function itself. This gives us 1/2 the integral from 2 to 1 of the quantity, x squared minus x plus 2 squared dEx. Expanding the square, we get a polynomial. It's a bit lengthy, but straightforward to integrate. The expanded form is x to the 4th plus 2x cubed minus 3x squared minus 4x plus 4. Now we integrate each term. This gives x to the 5th over 5 plus x to the 4th over 2 minus x cubed minus 2x squared plus 4x, all multiplied by 1/2. Evaluating this at the limits 1 and 2 requires careful substitution, especially with the negative signs. After simplifying the fractions inside the brackets, we get 1/2 times 81 over 10, which equals 81 over 20, or 4.05 cubic units. Finally, we find y bar by dividing a sub mx by the area A. This is 4.05 divided by 4.5, which is exactly 0.9 units. So, the centroid of the area under the parabola is at 0.5, 0.9. Notice that the x-coordinate of the centroid matches the axis of symmetry, confirming our earlier check. Our third example involves a more complex curve, an ellipse. The equation x squared over a squared plus y squared over b squared equals 1 defines an ellipse centered at the origin. We're asked to prove the area of 1/4 of this ellipse. The part in the first quadrant is 1/4 pi AB. First, let's sketch it. It's the region in the top right quadrant, bounded by the ellipse and the x and y axes. We'll use a vertical strip from x equals 0 to x equals a. This means we need the upper boundary y as a function of x. Let's rearrange the equation of the ellipse to solve for y. The area, a, is the integral of y dx from 0 to a. Substituting our expression for y, we get the integral from 0 to a of ba times the square root of a squared minus x squared dx. To solve this, we can pull the constant ba outside the integral and use a standard integration formula. The integral of the square root of a squared minus x squared is x over 2 times the square root of a squared minus x squared, plus a squared over 2 times arcsin of x over a. We need to evaluate this from 0 to a, plugging in the upper limit. A, the first term becomes 0, and we get a squared over 2 times arcsin 1. Plugging in the lower limit 0 makes both terms 0. Arcsin 1 is pi over 2, so we have ba times a squared over 2 times pi over 2. This simplifies to pi times a squared b over 4a, which is pi ab over 4. We have now proved that the area is indeed 1/4 PAB. This makes sense, as the area of a full ellipse is PAB, and we found 1/4 of that. Now that we have the area, let's find the centroid coordinates for our quadrant of the ellipse. Let's start with the x-coordinate. We need the area moment about the y-axis, a sub my. Using a vertical strip, this is the integral from 0 to a of x times y dx. This integral can be solved using substitution. Let u equal a squared minus x squared. Then do equals negative 2x dx. This means x dx equals negative 1/2 do. Substituting this into our integral, we get negative b over 2a times the integral of the square root of u do. The integral of u to the power of 1/2 is u to the power of 3/2 divided by 3/2. After simplifying and substituting u back to a squared minus x squared, we get negative b over 3a times a squared minus x squared to the power of 3/2 evaluated from 0 to a. Plugging in the limits, we get negative b over 3a times, or 0 minus a cubed, which simplifies to positive b times a squared over 3. Now we can find x bar. X bar is a sub my divided by the area A, which is a squared b over 3 divided by piab over 4. Simplifying this complex fraction gives us 4a over 3 pi. Halfway there. Now let's find the y-coordinate of the centroid. We need the area moment about the x-axis, a sub mx. Using our vertical strip, This is 1/2 the integral from 0 to a of y squared dx. We already found that y squared equals b squared over a squared times a squared minus x squared. Substituting this in, we get the integral of b squared over 2a squared times a squared minus x squared dx. Integrating term by term, we get a squared x minus x cubed over 3. Evaluating this from 0 to a, we plug in a and subtract 0, which gives a squared times a minus a cubed over 3. This simplifies to b squared over 2a squared is times 2a cubed over 3, which equals b squared times a over 3. Finally, we find y bar. Y bar is a sub mx divided by the area A, which is ab squared over 3 divided by pi ab over 4. Simplifying this gives us 4b over 3 pi. Notice the symmetry between the x bar and y bar results. So the centroid of the quadrant of the ellipse is located at 4a over 3 pi, 4b over 3 pi. This is a well-known result, and knowing it is another way to check your final answer. Our fourth example involves the area enclosed by two parabolas. Let's start by sketching the two parabolas. The first, y equals 2x minus x squared, opens downwards. Factoring out x gives y equals x times open parenthesis 2 minus x. Its x-intercepts are at 0 and 2. The second, y equals x squared minus 2x, opens upwards. Factoring gives y equals x times open parenthesis x minus 2. Its x-intercepts are also at 0 and 2. Notice that the second parabola is just the negative of the first. Let's find their points of intersection by setting their y values equal. This confirms they intersect at x equals 0 and x equals 2. Now we can draw our sketch. The first parabola is the upper boundary of the enclosed area, and the second is the lower boundary. Before we calculate, let's observe the symmetry. The enclosed area is perfectly symmetrical about the vertical line x equals 1 and the horizontal line y equals 0. Due to this symmetry, we can deduce that the centroid must lie on both of these axes. Therefore, the centroid's coordinates are 1, 0. The question asks us to prove the x-coordinate is 1, so our calculation should confirm this. A vertical strip is clearly the best choice here. The upper curve is always y equals 2x minus x squared, and the lower curve is always y equals x squared minus 2. Let's perform the calculation. The question specifically asks us to prove x bar equals 1, so we only need to calculate the area and the area moment about the y-axis. First, the area A is the integral from 0 to 2 of the upper curve minus the lower curve. Simplifying inside the brackets gives 4x minus 2x squared. Integrating term by term, we get 2x squared minus 3x cubed. Evaluating from 0 to 2 gives 8 minus 16 3, which is 83 square units. Now for the area moment about the y-axis. This is the integral from 0 to 2 of x times y1 minus y2 dx. Again, simplifying gives the integral of 4x squared minus 2x cubed dx. Integrating gives 4 3x cubed minus 1 cube x to the fourth. Evaluating from 0 to 2 gives 32 3 minus 8, which is 83 cubic units. Finally, we find the x-coordinate by dividing a sub my by a. And there we have it. Our calculation confirms our deduction from symmetry. The x-coordinate of the centroid is indeed 1. If we were to find the y-coordinate, we would find it as 0, confirming the centroid is at 1000. Our next example introduces using a horizontal strip, and it focuses on calculating the first area moment about the x-axis. First, let's find the intersection points. We can use substitution. From the first equation, we know y squared equals x. Substitute this into the second equation to get 4x equals 5 minus x. This gives 5x equals 5, so x equals 1. Now plug x equals 1 back into y squared equals x to find y squared equals 1, so y equals plus or minus 1. The intersection points are 1, 1, and 1 or 1. Now let's sketch the area. The graph y squared equals x is a parabola opening to the right. The equation 4y squared equals 5 minus x, or x equals 5 minus 4y squared, is also a parabola opening to the left with its x-intercept at 5, 0. The points 1, 1, and 1, -1 are where they intersect. We are interested in the area in the first quadrant, bounded by these two curves and the x-axis. we can see that the area extends vertically from y equals 0 up to the intersection point at y equals 1. For this shape, a horizontal strip is ideal. A horizontal strip extends from the left boundary to the right boundary. The right boundary is always the line x equals 5 minus 4y squared, and the left boundary is always the parabola x equals y squared. This is simpler than trying to use a vertical strip, which would require splitting the integration into two parts. Okay, we have our intersection points, sketch, and a horizontal strip. Let's calculate the area moment about the x-axis, a sub mx. We use the formula for a horizontal strip, which is the integral of y times x1 minus x2. dx1 is the curve on the right, x2 is the curve on the left. Our limits of integration are from y equals 0 to y equals 1. The right curve is x1 equals 5 minus 4y squared, and the left curve is x2 equals y squared. Simplifying the term in the brackets gives 5 minus 5y squared. Distributing the y gives us the integral of 5i minus 5y cubed die. Integrating term by term, we get 5 to 2y squared minus 5 4y to the power of 4. Evaluating from 0 to 1 gives us 5 minus 5 4, which is 5 4, or 0.25 cubic units. The problem also asks for the distance of the centroid from the x-axis. That distance is simply the y-coordinate, y bar. So we need to find y bar. To find y bar, we also need the total area A. The area is the integral of x1 minus x2 di from 0 to 1, which we've seen simplifies to 5 minus 5y squared. Integrating gives 5y minus 5 to 3y cubed. Evaluating from 0 to 1 gives 5 minus 5 3, which is 10 to 3 square units. Now we can find y bar. It's the area moment about the x-axis divided by the area, 5 4 divided by 10 power 3. This simplifies to 3/8, or 0.375 units. So the first area moment about the x-axis is 1.25 cubic units, and the distance of the centroid from the x-axis to y bar is 0.375 units. Our sixth example involves a triangular area bounded by two lines and the x-axis. Let's start by finding the vertices of this triangle. First, the intersection of the two lines. Setting y equals y gives x minus 2 equals 2x minus 6, which solves to x equals 4. Plugging back in, y equals 4 minus 2, which is 2, so the first vertex is 4, 2. Next, let's find where the line y equals x minus 2 intersects the x-axis, y equals 0. Setting y to 0 gives 0 equals x minus 2, so x equals 2. The second vertex is 2, 0. Finally, where does y equals 2x minus 6 intersect the x-axis? Setting y to 0 gives 0 equals 2x minus 6, so x equals 3. The third vertex is 3, 0. So we have a triangle with vertices at 2,000, 3,000, and 4,2. Let's sketch it. Now, which strip to choose? A vertical strip here would be problematic. From x equals 2 to 3, the upper boundary is y equals x minus 2. But from x equals 3 to 4, the upper boundary changes to y equals 2x minus 6. This would require two separate integrals. A horizontal strip is much better. For any height y, the strip always extends from the line y equals x minus 2 on the left to the line y equals 2x minus 6 on the right. This means we only need one integral. For a horizontal strip, we need our functions as x in terms of y. Rearranging e equals x minus 2 gives x equals y plus 2. Rearranging e equals 2x minus 6 gives x equals 1/2 e plus 3. Okay, we have our horizontal strip and our equations in terms of y. Let's find the area A. The area A is the integral from y equals 0 to y equals 2 of the right curve minus the left curve. Simplifying inside the brackets gives 1 minus 1/2 y. Integrating gives y minus 1/4 y squared. Evaluating from 0 to 2 gives 2 minus 1, which is 1 square unit. It's always a good idea to check this result. The area is a triangle with base from x equals 2 to 3, which is 1 unit, and height up to y equals 2. So, area equals 1/2 times base times height equals 1/2 times 1 times 2, which is 1. The integral result matches our geometry check. Now let's find the area moment about the y-axis, a sub my. This is 1/2 the integral from 0 to 2 of the right curve squared minus the left curve squared. Expanding the squares gives 1/4 y squared plus 3y plus 9 minus y squared plus 4y plus 4. Simplifying inside the brackets gives -3/4 y squared minus y plus 5. Integrating and evaluating from 0 to 2 gives us 1/2 times -2 minus 2 plus 10, which is 3 cubic units. Now for the x-coordinate. X bar is a sub my divided by a, which is 3 divided by 1. So x bar equals 3. We're almost done with this problem. We have x bar equals 3. Now we need to find y bar. We need to calculate the area moment about the x-axis, a sub mx. This is the integral from 0 to 2 of y times the right curve minus the left curve, d. We already simplified the bracketed term to 1 minus 1/2 y. Distributing y, we get the integral of y minus 1/2 y squared d. Integrating gives 1/2 y squared minus 1/6 y cubed. Evaluating from 0 to 2 gives 2 minus 4 3, which is 2/3 cubic units. Finally, we calculate y bar. Y bar is a sub mx divided by a. So y bar is 2 3. Our centroid for this triangle is located at the point 3 2 3. For our final example, we will determine the x-coordinate of the centroid for a region bounded by a hyperbola, the axes, and a horizontal line. Let's begin by sketching the region. The equation is a hyperbola. The term x squared over 9 is positive, which means this is a horizontal hyperbola with vertices at plus or minus 3 on the x-axis. We are interested in the first quadrant, so the relevant part of the curve starts at x equals 3 on the x-axis and opens to the right and up. The area is bounded by this hyperbola, the x-axis, the y-axis, and the horizontal line y equals 2. Let's sketch this bounded region. This is our shaded region. Again, a horizontal strip from y equals 0 to y equals 2 will be easier to work with than a vertical one. So we need the hyperbola's equation with x as the subject. Rearranging the equation gives x equals 3/2 times the square root of y squared plus 4. We take the positive square root because we are in the first quadrant. The problem only asks for the x-coordinate of the centroid x bar. For that, we need the total area A and the area moment about the y-axis, a sub my. Let's start with the area. It's the integral from 0 to 2 of our expression for x, which is 3/2 times the square root of y squared plus 4 di. This integral requires another standard formula. The formula for the integral of the square root of x squared plus b squared is x over 2 times the square root of x squared plus b squared, plus b squared over 2 times the natural log of the absolute value of x plus the square root of x squared plus b squared. Applying this formula to our integral, where y is our variable and b squared is 4, we get a rather long expression to evaluate from 0 to 2. Substituting 2 for y gives 3/2 times the quantity, square root of 8 plus 2 times the natural log of 2 plus the square root of 8. Substituting 0 for y gives 3/2 times, 2 times the natural log of 2. Calculating this gives an area A of approximately 6.8868 square units. Now that we have the area, let's calculate the area moment about the y-axis, a sub my. For a horizontal strip, a sub my is 1/2 the integral from c to d of x squared di. We found earlier that x squared equals 9/4 times the quantity, y squared plus 4. Substituting this in, we get the integral from 0 to 2 of 9/8 times y squared plus 4 d. Integrating term by term gives 9/8 times the quantity y cubed over 3 plus 4y. We evaluate this from 0 to 2. Plugging in 2 gives 9/8 times the quantity, 8/3 plus 8. This simplifies to 12 cubic units. Finally, we can find x bar. X bar is a sub my divided by a. This is 12 divided by 6.8868, which gives us approximately 1.742 units.